Hello everyone, so in this video we are going to start with sentence transformers. We are going to study what it is, and in the next video we are going to do an implementation. So this is the paper. So sentence BERT, SBERT also as they say, it basically helps to convert sentence to embedding. Okay, so we know something like word to vec, which can convert your words to embeddings. Okay, so you have a word and it will have a embedding, which is, let's say, n dimensional. Okay, and you can have glove, you can have other things as well. Sentence embedding, instead of a word, it takes a sentence, and you already know that a sentence can be of any length, so arbitrary length, and then convert it into a embedding of fixed length, let's say m. So this is one thing that it does. So as I said, sentence can be of any length and can be arbitrary length, and it will convert it into an embedding which is of a fixed length embedding, which means doesn't matter what your sentence length is, give it and you will get a very nice mathematical representation of that. Now, what is the goal? Why do we need to do that? Well, there can be many goals, but in this case we are going to do one thing, which is finding the similarity between two sentences. So let's say there is S1 and there is S2. Now there are multiple ways of finding similarity. Some are easier than the others, but in this case we are going to see if they are more similar, our score will be closer to 1, or if they are very, let's say different, their score will be closer to -1. Okay, so this is the idea. Let's go ahead and do that. So how do we do this? Very complicated question. So approaches, three approaches are there. I'm going to go very fast. So first approach is you have a BERT algorithm and then you give two sentences to it. Okay, second one is you give one sentence. We will see how this happens, and then finally use glove or word to vec. So let's quickly discuss what is the first approach. As I said, you take first sentence and second sentence, you give it to the BERT algorithm and then predict a similarity score. Now I'm not getting too deep into the implementation, but what I can tell you is that there is a problem with this approach, and the problem is if there are n sentences, okay, and n is large, let's say n is 10,000, okay, or let's even take 1,000, okay, then how many comparisons you have to do? Remember, this is going to take two sentences, pair of sentences, so they are going to be n into n minus 1 by 2, which is O of n square, which means if this is 10 to the power 3, then comparisons will be 10 to the power 6. So this is only 10 to the power 3. What if this is 10 to the power 6? Then the comparisons is going to be 10 to the power 12, something like that. Okay, divide by 2, whatever, very close to this. So the idea is this is not going to scale. Okay, so this is too slow. Okay, scalability, and why it's not going to scale? Because it's too slow. Now let's go for the second approach. Okay, let's do something like let's just give one sentence to the BERT and then get the embedding. So if there are 1,000 sentences, we only need to give 1,000 times 1,000 sentences, each sentence at a time to BERT, and 1,000 embeddings will be created. This hopefully should solve the problem. And what you do once that both embeddings are available, you find a similarity score. Let's say for example your cosine similarity. It could be any metric. Okay. Now there is one problem with this. The problem is they tried this. Okay, this is not something that they haven't done it. When I say they, I mean the researchers, and they found it's a very bad idea. It gives you very bad performance, even worse than glove and word to vec. So how do we use the third approach, which is using word to vec? Basically, you take a sentence. A sentence is a collection of words, obviously, and you feed each and every word to the word to vec. And what you generate is for every word. So let's say there is word 1, word 2, word 3 up to word n. Then here you can see for every word 1, word 2, word 3 up to word n, there is an embedding. Okay, and that is true for all the words. Okay, after that, what do you do in order to find the similarity? Well, first of all, you have to, obviously this is a matrix, this is not a this is not a one-dimensional vector. So what do you do? Sorry, n-dimensional vector. So what do you do over here is you average, and this is pooling. We will see in the next slides, but basically what you do an average. So you do an average of E11, E21, E31 for every to say the first dimension, En1, and you get 1 over here, which is the average of all of this. Same thing for this row, and all these rows. Okay, so you get this particular embedding over here. Similarly, you can do the same thing for a sentence 2 also, same formula, and then use these two and then calculate the similarity score. Now, what is the problem with this? The problem is there is nothing called as context over here. No context, as each word is independent. Remember, when you use word to vec, it focuses on words. It does not care what happens after that particular word and what happens before that particular word, which means context is not there, which means these are obviously not going to perform as good. So what is the solution? Solution is something called as the Siamese network. So what is the Siamese network? It basically says we are going to use the same model, but we are going to use the different data. Now, you might have already thought this, but actually we were able to solve a great problem in approach 2. But here we are going to change that approach a little bit. So if you remember in approach 2, we were only giving the sentence. Here what we have done is we have prepended a CLS token, okay, something like what happens in BERT. And same thing for sentence 2 also, okay. So we are going to prepend this particular token for both the sentences, then ask BERT to convert it into embeddings, okay, and same thing over here. So now we have two embeddings, right? Now we will see pooling. I have already explained, but this is something that you need to keep in mind. So obviously the sentence was given, this was embedding of 1. Now if you remember in the embedding of 1, the previous time we did not have this CLS token. Now since we have given the CLS token over here, we get one extra embedding over here. Again, do the same thing. What you do a mean pooling, which is you go over here and average this and you get particular E1. Same thing for this, you go and pool this one, you get E2. Same thing all the way to M and you get EM. Let's call this U. Can't we do this for the same for the second sentence? Same idea. You find the EMB2 embedding 2 and again do the pooling and then call it V. So the previous one was U, this one was U, and this one is V. Okay. Now what we can do? We can now train the Siamese network. How? Now this is very important. This is from the paper. You gave one sentence. This is exactly what happened over here. Okay. This is shown in the diagram over here. You took a sentence, you gave it to BERT, you did the pooling that I have already explained, and let's call the final embedding as U, which we have already seen. Same thing for V. Now you take these two vectors and then try to concatenate. So let's say this is the first vector, this is called U, this is called the second vector, which is V, and you know how to do, if you have two vectors U and V, you know how to do U minus V, right? So now you will do this, you will find another vector which is U minus V. Okay, so you concatenate them in this dimension. After that, what do? Is you basically take this and then have a linear layer over here. As you can see, there is a linear layer over here. Okay, let's say this has m dimension, which we have already seen. So this becomes 3m dimension, and you have a linear layer over here. Let me draw like this, linear layer, which takes 3m dimension and then converts it into k. Now k can be anything. So okay, so into k. This is a linear layer, n dot linear, basic stuff, right? We already have seen all of this. And then you have to do some classification, whatever the classification is. I'll give you one example of that. Okay, some classification and then softmax classifier, cross entropy, loss, and then backpropagation, all that you already know. So what is the task that we are optimizing for? It is called natural language inferencing. Okay, so you're given sentence 1 and then you're given sentence 2, and then you have to say, does sentence 2 entail sentence 1? Does sentence 2 contradict sentence 1, or is it neutral? So let's say, for example, I had a coffee is sentence 1, and today is let's say Tuesday. Does it entail, does it if I say today I had a coffee, does it mean that today is Tuesday? No, I can have coffee any other day, any day of the week. If I say it's a contradiction, is it a contradiction? No, there's nothing. So basically it's a neutral, right? So which means this is class 3. So this is how you train this particular model, and once you are done with all of this, you can throw this, you can only keep the BERT. Okay, so finally what will happen is you will have your trained BERT model over here, BERT, which is your sentence transformers. Okay, then you keep passing in your own sentence and keep getting your embeddings out of it, which is going to be very, very important, and it will have all the context, and you don't have to do in O of n square. Okay, so I hope you understood. If you like, please like the video. Thank you very much, and bye.